Hi, I'm Ticha Sethapakdi, and today I will talk about our system for designing and fabricating polarized light mosaics. As you know, conventional painting techniques rely on applying pigments, inks, and dyes to surfaces to create artistic imagery. But in the 1960s, some artists explored a new medium for painting, light. In particular, artists discovered materials with special properties that allowed them to change their appearance depending on how polarized light passes through them. And these so-called birefringent materials turn out to be inexpensive and easy to find. The mosaic on the left was made with packaging tape, while the one on the right was made with cellophane film. You can make one yourself by sandwiching pieces of the birefringent material between two polarizers. But what's most compelling about polarized light mosaics is the ease with which you can create color-changing effects. For example, you can achieve the effect here by rotating the image layer, and you can achieve the effect here by rotating one of the polarizers. However, to the best of our knowledge, there are no formal specifications or support tools for this medium. Polarized light mosaics are made entirely by hand, and mosaicists often have to resort to experimentation before they know what colors they have access to or what effects are feasible. And in practice, very few people have explored this medium, in part because of how challenging it is to master. This video shows a master polarized light mosaicist at work, and you can see how it's quite an intricate process. So to address these challenges and lower the barrier to entry for making polarized light mosaics, we built an end-to-end system that allows users to design and fabricate these mosaics with custom color-changing behaviors. In this work, we formalized the set of mosaic constructions and the color-changing effects enabled by them. I won't go into all of them today, but I just wanted to go through the basic working principle and the most archetypal examples. The most basic mosaic uses a single layer of cellophane sandwiched between the two polarizers, which results in a single colored design. For clarity, we use the term analyzer to refer to the topmost polarizer. When both polarizers are aligned with the cellophane's strain direction, the mosaic will appear colorless, and at 45 degrees, it reaches maximum saturation. The mosaic alternates between colored and colorless at 45-degree increments. And since the opacity of the mosaic depends on its angle relative to the polarizers, you can achieve the same effect by either rotating the mosaic or rotating both polarizers at the same time. The orientation of the polarizers with respect to each other also affects the appearance of the design. Colors under parallel and orthogonal polarizers are complementary to each other. Notice how the background changes to black when the polarizers are orthogonal to each other. And this is because the orthogonal polarizers block light, while parallel polarizers let light pass through. We can create multicolored designs by stacking multiple pieces of cellophane together and then arranging them to form an image. The aforementioned color effects work in the same way. What happens if we wanted to fade two mosaics into each other? Recall that mosaics are colorless at 0-degree rotations and reach full saturation at 45-degree rotations relative to the polarizers. By positioning the mosaics at a 45-degree offset to each other, we ensure that one mosaic is fully saturated only when the other is fully colorless. The last effect I want to talk about is masking. The mask is just a third polarizer that is inserted between the topmost mosaic and analyzer. Its visibility depends on its alignment relative to the analyzer. Remember that polarizers will block light when they are orthogonal to each other. Thus, the mask is fully opaque when it is orthogonal to the analyzer and transparent when they are parallel. Now that you have an understanding of the basic color-changing effects, here is a brief walkthrough of how a designer might use our system to create a mosaic. Upon startup, Polygon Studio shows users design templates based on the 4 core polygon constructions. The template that the user picks determines the complexity of their final design. So in this case, the user is picking a double mosaic and mask construction. Once users select a design template, Polygon Studio loads the template files into the main window. Users can then modify the existing template files or load custom designs into the interface. So in this case, the user is replacing the template design with one that they made. When the user imports their design, the interface maps the colors in the design to the closest matching colors under aligned polarizers. So in this screen, the user can explore the available color palette based on their supply of cellophane and adjust the colors in their mosaic. So hovering over a swatch in the available color palette shows a tooltip that shows the quantity and the types of cellophane that the color is made from. The user can also switch between using the colors under aligned or orthogonal polarizers, as well as filter colors if they want to work with a more restricted palette. They can also change specific color assignments. When they are satisfied with the colors in their new design, the main window is updated accordingly. We also provide an interactive mode, which allows users to build intuition on the color changing effects. The left side of the interact window shows the mosaic decomposed into its constituent components, represented as adjustable knobs. The right side shows the effect that those rotations have on the polygon's appearance. And we also provide a way to show users how their mosaic might look with their physical object using a custom plugin for Rhino. When the user is done with their design, they can export files that are ready for fabrication, and then follow the steps in our custom fabrication process. The process of fabricating a mosaic involves loading a fabrication file, placing the required cellophane sheet into the laser cutter, running the laser cutter, peeling the outer areas of the sheet, and repeating until all files are fabricated. Note that the mosaic holds together because at each fabrication step, the heat of the laser cuts and lightly welds the shapes to lower layers. To wrap up, I'll showcase a few applications we've created with our system. Here's the design from the walkthrough made into a pair of festival glasses. I'd imagine they'd be fun to wear at raves. And this is a passive display that we incorporated into a sliding glass door. So when a person slides one side of the door open, it reveals a message that reminds the user to close the door. We also made this tangible visualization of how COVID hotspots in the US changed between July and August 2021. And here's an animated clock face. In conclusion, creating digital fabrication processes and design tools for traditional making practices has the advantage of preserving art forms that are typically only accessible to skilled individuals. So we hope that Polagons can expand the community of modern polarized light mosaicists, and by making the process accessible to makers, add a new programmable material to that diverse palette of options in HCI. Thank you.